Welcome back. In our previous meeting, we discussed why we often want to compare biological sequences. In this segment, we will relate to the details of how such sequence comparisons are performed. Let's look at the unresolved example from the last segment, in which we wish to characterize the degree of similarity between two sequences. We can take the obvious approach and compare the first letter to the first letter, the second to the second, and onwards from the beginning to end. Using this simple method, we see that out of 17 amino acids, there are 5 matches. So we can divide 17 by 5 and conclude that the sequences are about 29% similar or 29% identical. Actually, similarity and identity are not the same terms. We will discuss this issue in the next segment. In any case, when we look at sequences, and especially if we look at them as words with meanings, there was a small gap. And here is a smaller gap. We would come to the intuitive conclusion that they are actually more similar than the figure 29% suggests. How can we capture this similarity? We can do it using a computational approach called dynamic programming. This method can not only calculate the similarity between sequences, but can also align them in such a way that their similarity will be most evident. Such alignment can be performed to compare either nucleotide or amino acid sequences. We will start our demonstration with 2 short DNA sequences, AGTGATA and ATGAGTC. How similar are they, and what are the mutational steps that most likely transformed one into the other? The dynamic programming approach are implemented by many publicly available software packages, as you will see in the practice lesson. Nevertheless, it is useful to understand the steps through which such a comparison is performed. We start by preparing a matrix, writing the sequences along the x and y axis, adding a blank row and column before the sequences, and initiating the matrix by putting a 0 in the upper leftmost cell. In order to fill the matrix, we need a set of weights that will reflect the costs that we will assign for the different types of sequence matches or differences. Here, we start with a simple set with somewhat arbitrary uniform cost. In this example, we will assign a score of +2 for a match and a cost of -1 for all types of mismatches or mutations, including insertions, deletions, and substitutions. The algorithm may be easily modified to assign different costs to different types of mutations or different amino acid substitutions, as we will describe later. First, we fill the 0th row and column. The first cell we need to fill in represents aligning the nucleotide A with an empty character. This can be done by deleting the A. Since the cost of deletion is -1, the cell will be assigned the value of -1. We look at the next cell, which represents aligning the first 2 nucleotides of the horizontal sequences, A and G, with an empty string. Here we require 2 deletion operations, so the cost will be -2. We continue to fill in the entire 0th row in the same way. Then we start filling the 0th column. The first cell represents aligning an empty character with A, which requires an insertion operation with a cost of -1. We continue to populate the entire column in a similar way. Note that the value of the first row and column are dependent only on the cost of the insertion and deletion weights, and not on the sequences being compared. Now, we turn to fill in the body of the matrix. We will work row by row from left to right. In order to determine the value of each cell, we need to look at the values of 3 neighboring cells: the cell on the left, the cell above, and the cell on the left upper diagonal, and pick the cell that will yield the maximal value. If we choose the cell on the left, we need to take its value and then pay the price for a deletion. If we come from above, we need to take its value and pay the price for an insertion. If we come from the diagonal, we have to look at the nucleotides that intersect at the cell. In our case, it is A versus A. So we have a match. And we can take the value of the diagonal neighbor and add the value of a match, which in our current scheme is +2. If the nucleotides that intersect are different, then we would still take the value of the diagonal cell and pay the cost of a substitution. So we have three options. Coming from the left, the value would be -1, -1, that is -2. If we come from above, we have the same values, -1, -1, which is -2 again. But if we come from the diagonal, noticing that the two intersecting nucleotides match, we have actually 0 + 2, which is 2. As we are looking for a maximum, we will choose a value of +2 for our cell. We will continue to fill in the rest of the matrix in a similar way. Let us pause here. First, let's explain again why this cell was assigned the value of +3. +3 is the maximum value that we can obtain when comparing the sequence changes relative to its three neighboring cells. On the left with a value of 1 - 1, which is 0, coming from above with 0 - 1, which is -1, or coming from the diagonal with matching nucleotides yielding a value of 1 + 2, which is 3, which is clearly the maximum. Note that this cell represents the alignment of the first three nucleotides of the horizontal sequence with the first two nucleotides of the vertical sequence. This alignment requires two matches and one mismatch. So according to our weights, the alignment should indeed have the value of 2 + 2 - 1, which is +3. The mathematical proof is beyond the scope of our course, but we can show that if we continue the process until we fill in the entire matrix, the value of the cell at the bottom right of the matrix represents the value of the best global alignment between the two sequences. In this example, the numerical value of the alignment under this set of cost is +7. Usually, we don't attribute much significance to this value by itself, but the matrix can guide us in calculating and presenting the alignments that represent this optimal sequence similarity. To this end, we need to backtrack the trajectory in the matrix. We start from the lower right cell and we ask which of the neighboring cell is responsible for its value. Here it is a diagonal cell, because if we would come from the left or top paying the required penalty, the value would have been 6 and not 7. We continue, and here we realize that it must have been the diagonal cell again. Next, the cell that is responsible for the fact that we have a value of 6 here must have been the cell on top, which has a value of 7. Note that we could not come from the diagonal since the intersecting nucleotides do not match, and thus coming from the diagonal would result in a value of 3. We will continue all the way until we reach the cell in the upper left corner. Note that if a cell could have been marked with the same value by two neighboring cells, we may choose either one. The final step is to use the trajectory to write down the alignment. We write the two aligned sequences, one on top of the other, from right to left, as we do in Hebrew. We write the sequence display horizontally in our matrix on top of the vertical sequence. When the trajectory is diagonal, we write the nucleotides from both sequences, whether or not they are the same. We continue on the diagonal using nucleotides from both sequences. When the trajectory is vertical, we take a nucleotide only from the vertical sequence, which is on the bottom row, and insert a hyphen to represent a gap in the horizontal sequence, which is on the top row. The trajectory continues diagonally, so we use nucleotides from both sequences. When the trajectory is horizontal, we use a nucleotide from the upper sequence and insert a hyphen in the lower sequence. The process continues until we arrive at the top left cell. Now we can go over the alignment and mark the identical nucleotides. Since the length of the alignment including the gaps is 8 characters, and we found 5 identical nucleotides, we can say that the sequences are 5 divided by 8, means 62.5% identical. This is a basic pairwise sequence alignment algorithm. In practice, we use several extensions of the basic algorithm, which we will discuss in the next segment. I realize that this presentation was a bit detailed, so thank you for bearing with me.